Hello and welcome back. Today we are going to look at reverse linked list 2. The problem statement can feel a little tricky at first, but the idea is simple. This is an advanced version of previous linked list problem. Last time we reversed the whole linked list. This time we only reverse a part of linked list. For example, in example 1, we are asked to reverse the section from the position 2 to position 4. So the sublist 2, 3, 4 should become 4, 3, 2. After that, we need to connect this reversed part back into the original list. So the final result should be 1, 4, 3, 2, 5. If you have not watched the previous reverse linked list video yet, I recommend checking that first. Because in that episode, we covered the basic linked list operations and the three-pointer reversal method. Today's solution builds directly on those ideas. Let's first think about this problem using the method from last time. In the previous episodes, we used three pointers: pre, current, and next, to reverse the whole linked list. So for this problem, can we first move to the left position, then use the same method to reverse the part from left to right? In theory, yes, but in practice, this gets a little messy. Let's do a quick sketch. Suppose we want to reverse the section from 2 to 4. Yeah, after reversing this section, it becomes 2, 4, 3, 2. This inner reversal can be done with the three-pointer method from last time. But after the reversal is finished, we still need to connect this part back to the original linked list. At the front, we need to remember the node before left, and that is, we can call it pre-left. At the back, we also need to remember the node after right. We can call it post-right. These names are not fixed. You can name them however you like, but these two nodes must be remembered. And inside the reverse section, we will also have left and the right. After reversing, right becomes the new head of the section. So we have pre-left dot next equals right. So that is this link. And left becomes the tail of the section, so we need left dot next equals to post right, and that is this link. That's the basic process if we use the previous method. Now let's count how many references we need. First, we need pre-left and the post-right. And then we need reference for the head and the tail of the section we are reversing. They are same as the left and the right. And during the actual reversal, we still need pre, current, and next. Some of these references can overlap if we are careful, but overall, this approach still needs about 5 references. Okay, so this is still the ideal case, We have not even handled the boundary cases yet. For example, if the section ends at the last node, then the post-right is none. And that is the case. And this is the post-right. If the section starts from the head node, then pre-left may also be none. And that case is left is here, so the pre-left will be none, because there's no node here. So with previous approach, we need multiple references, and we also need to handle several edge cases. The whole solution becomes quite tedious. So here's the question. Is there a way to reverse a sublist using only 3 references without doing a separate reconnect step? And the answer is yes. And that method is called head insertion. And what does head insertion mean? It means that we take the nodes that we need to be reversed and insert them one by one at the front of the sublist. That's the whole idea. Let's use the same example. We want to reverse 1, 2, 3, 4, 5 from position 2 to position 4. First, we need to mark left and right. Then we find the node before left. Here, left is node 2, so the node before it is node 1. We call this pointer pre. Important detail: during the whole header insertion process, pre does not move. This is different from the 3-pointer method from last time. In the previous method, after each small step, all 3 pointers move forward together. But here, pre always points to node 1. Then we need another pointer called current. Current points to the node we are currently working on. In this example, current points to node 2. At this point, the initialization is done. Now, let's list the 4 core lines of header insertion. Okay, these 4 lines are the heart of this problem. Now, let's walk through them one by one. The first step is the same as the last time. Save the next node. Here, next points to node 3. The second step is current.next equals to next.next. This means current skip over next and points to the node after next. We use another color. In this example, current is node 2, and next is node 3, and next is node 4. So now node 2 points to node 4. At the same time, the original link from node 2 to 3 is disconnected because next pointer can only point to one node at a time. The third step is next.next equals pre.next. Here, next is node 3 and pre.next is node 2. So this line makes node 3 point to node 2. At the same time, the old link from 3 to 4 is disconnected. The fourth step is pre.next equals next. This makes node 1 points to node 3. At the same time, the old link from 1 to 2 is disconnected. Now, if we remove the old links and the followed new arrows, the list becomes to 1, 3, 2, 4, 5. And the path is. So after one round, the small section 2, 3 has already been reversed into 3, 2. And notice what is next here. We only use 3 pointers, and we did not need a separate reconnect step. Now let's continue one more round. At this point, pre is still node 1, and current is still node 2. This is the key difference between header insertion and the standard 3-pointer reversal. In header insertion, pre and current stay fixed during the inner loop. The one that changes each round is next. Now we need to do the same 4 lines again. First, we need to mark next, and that is node 4. And second, current.next equals to next.next. Node 2 skips over node 4 and points to node 5. And at the same time, we disconnect the original link. Now, the third step, next.next equals to pre.next. Now, next is node 4, and pre.next is node 3. So node 4 points to node 3. And disconnect original link. And the fourth step, pre.next equals next. node 1 now points to node 4 and disconnect the original link. If we straighten the list again, it becomes to 1, 4, 3, 2, 5, and the path is okay, and that is exactly the result we want. So after 2 rounds of this small operation, the sublist has been reversed, and we still only use 3 pointers. Now there's one thing I need to emphasize again. The order of these 4 lines cannot be changed. Linked list programs are very sensitive to pointer update order. If one line happens too early, you may lose part of the list or accidentally create a self-loop. Let's look at an example. Now suppose current is node 2 and next is node 3. If we accidentally swap the second and third line, they're like this, and run this first, next equal pre the next. Then node 3 point back to node 2. And now if we run current to next equal next to next, and what is next to next at the moment? And that is node 2 itself. So node 2 points to itself. We create a self-link, and the rest of the list is lost, and the whole structure is broken. Okay, let's look at another run order. If we swap the third and fourth line, suppose we have already completed the first and then the second line, and that is we already create this link. And if we run the last line too early, pre the next equal next, and that is this link. Okay, so the next to next, pre the next, and now what is pre the next? And that is node 3 itself. So again, we create a self loop. So the order is very important. This is the same point we emphasized in the previous episode. When working with linked lists, pointer orders matters a lot. Now you may wonder, how do we remember these 4 lines? There is a small pattern. Let's look at the start and the end of each line. You can see current to next, current to next, next to next, next to next, pre to next, pre to next, and next, next. We can see the end of one line is same as the beginning of next line. So this is easy to remember because we only need to remember the first line. Then we can use this rule to find the formula. Now, so we can draw a sketch. First, we save next. We execute the first line. Once we have saved the next thing we need to change is current to next, because the beginning of next line is same as the end of the previous line. So you can easily write current to next here. So the problem is what it equals to. If you forget what current next should become, draw a teeny sketch. In this step, we need to reverse 2 and 3. After this reversal, the list should become 1, 3, 2, 4, 5, right. So now, if you forget what's the next node of node 2, just look at the completed sketch. The next node after node 2 is node 4. That means the second line is current to next equal next to next. And that is here, here. Yeah, Now notice something nice. The end of second line is next or next, and that becomes the start of third line. Using the same approach, node 3 points to whatever comes after pre, which is node 2. So the third line is next or next equals to pre or next. And finally, we move next to the front of reversal section. If you draw this a few times, the 4-line pattern becomes much easier to remember. Now that the idea is clear, let's see it in action in Algo Demo app. Here is our linked list. In this demo, we are reversing the path from node 3 to node 6. First, we initialize the pointers. After initialization, current points to left and pre is node 2. Next already points to node 4. Now we step forward. Since next is already initialized, the app directly runs the second line. Current next equal next to next. So node 3 skip node 4 and points directly to node 5. And next to next equals to pre to next. This makes node 4 point to node 3. And finally, pre to next equals next. This makes node 2 point to node 4. At this point, one small part has been reversed. If we straighten the linked list, we can see that this part has already changed direction. So we do the straighten. Then we keep repeating the same process until the target section is fully reversed. After the loop finishes, the partial reversal is complete. Now you can see the algorithm has complete. Now let's talk about edge cases. The demo we just saw reverse a section in the middle of the list. But sometimes the section may start from the head or end at the tail. If the section ends at the tail, the algorithm can handle it naturally because the last node next can become none. But if sections start from the head, we need one extra trick. We create a dummy node, sometimes show as P, before the real head. Then we make P dot next equals head. This dummy node helps us handle the cases where left is 1. At the end, instead of return the head, we return P dot next, because P dot next is the new head of the reversed list. Let's look at an example where we reverse the whole list from node 1 to node 8. In this case, pre starts at the dummy node P and current start at node 1. Yeah. And this is exactly why the dummy node is useful. Now we let the animation run automatically. So when the algorithm finishes, the whole linked list has been reversed. At this point, P.next is the answer we need to return. So the key takeaway for this episode is these 4 lines of header insertion. Remember the pattern between the end of one line and the beginning of the next line. And if it still feels abstract, draw a small example a few more times or watch the transformation in Algo Demo app a few times. Once you see the pointer movement clearly, this solution becomes much easier to remember. Alright, that is for today's algorithm. Okay, the demo you just saw that was made with Algo Demo. It's an algorithm visualization app I built personally. It covers a wide range of common, frequently asked, and popular algorithms. You can step through the code line by line and watch how the data structures and the variables change at each step. You can also drag the progress bar backwards to review any part you missed. The code is highlighted at real time, and you always know which line is being executed. The download link is in the description. Okay, see you in the next one.